So hello everyone, welcome to my presentation. Actually, I updated the title a little bit, so to cover a wider range. So the presentation is about the LMB, Augmenting PCIe Devices with CXL-Linked Memory Buffer. I'm Tao Lv from DapuStor. So DapuStor is a provider of SSD for data centers. This work is actually motivated by the need to address the DRAM shortage in future ultra capacity SSDs. Since the onboard DRAM in SSDs is insufficient to store the logic to physical page mapping table, this motivated us to find new solutions to this challenge. And through our exploration, we simply noticed that the L2P table is not only facing the challenge, the SSD is facing a challenge, and any of the PCIe device actually facing the DRAM shortage issues. That's why today I was discussing opportunity to overcome this issue. So the solution lies in CXL. This is an overview of what we will cover today. We'll start by examining the memory shortage issues of PCIe devices. Next, I will explore the CXL memory expander. I believe it's an efficient way to supplement PCIe devices with more memory. We'll then dive into the LMB architecture, showcase how it can effectively solve device memory shortage issues. I'll further present a case study to illustrate the practical use of the LMB to supplement giant SSD with more DRAM, so as to enable the 4 KB fine-grained page mapping as the best practice. Then I will briefly discuss other potential scenarios and the use case that the LMB may cover, such as the memory semantic SSD, the KV SSD, and even the GPU. Finally, I will wrap up with a summary. So for SSDs, the NAND flash capacity grows much faster than the corresponding DRAM. Even for today's 64 terabytes SSDs, actually it has to adopt the 16 KB mapping granularity, simply because there's not enough DRAM to store the L2P table. So, instead of the 4 KB, we have to cut the L2P index size. And some research work actually proposed using the NAND index. That's a kind of machine learning models to reduce the index size. But all these mechanisms, either the notch page or the NAND index, they suffer from the performance degradation, especially for the random write. So similarly, the GPU are also facing an HBM shortage. Although a single GPU can have up to maybe 140 gigabytes of HBM, it's still not large enough to support the training and the inference of large AI models. Specifically, loading and training models with 1 billion parameters requires about 16 to 24 gigabytes of HBM. And we know that today's the large language models can have over 100 billion parameters. So the HBM is simply not large enough. And during the LLM inference, the KV cache is very huge, and the HBM cannot accommodate it. So for the large language models, simply doing the inference, it will have to use either the host memory or SSD as a swapping mechanism to mitigate the HBM shortage issue. But the cost is the GPU underutilization. So one might wonder why we cannot just add enough memory modules to this device. So the root cause is that the PCIe device is primarily due to the physical constraints. So the design and the form factor of this device limit the addition of more memory modules. So simply there's not enough room to add memory modules. And the CXL, or the Compute Express Link, I believe it's an opportunity because there's not enough room. We have to trade the latency for rooms, right, to add more memory. CXL actually shows multiple good features. First, it has a no access latency of around about 200 nanoseconds, which is just a couple times of the local DRAM latency. And second, the CXL provides a scalable architecture, offering the flexibility to expand memory as demands grow. Third, the CXL supports sharing resources across multiple devices, allowing for efficient sharing and reducing the need for excessive onboard memory deployment. So CXL is poised to revolutionize how we deploy and manage memory in PCIe devices for large systems. We propose the linked memory buffer, which leverages CXL memory expander to augment PCIe device with additional memory. Memory buffer is not a new term or new concept at all. For our SSD guys, we know that previously we have the controller memory buffer, we have the host memory buffer. So LMB, I would say, is a natural extension of the CMB and the HMB in the CXL era. At its core, the LMB architecture is a memory expander, which adds DRAM to the systems. As the figure shows, the CXL and the PCIe device can access the memory resource through various paths, depending on the protocol support of the platform and the devices. So to make the LMB work, of course, we need to enable efficient resource access and management. LMB can potentially support a wide range of applications. We have employed the LMB architecture for large L2P index for giant SSDs, where the LMB enables fine-grained page mapping with no latency. I will elaborate this case study later. LMB can also be used to enhance the efficiency of DPUs through providing more data buffer to DPU, since the DPU buffer size significantly impacts the data processing performance. Additionally, in the realm of AI and machine learning, LMB allows for the efficient deployment of large models, overcoming the memory constraints that currently limit GPU capabilities. These scenarios highlight the transformative potential of LMB in addressing the memory challenges faced by modern storage and computing systems. So now let's look at a case study that illustrates the impact of LMB in ultra-capacity SSDs. So one critical aspect of SSD performance is the L2P page mapping. And the emerging ultra-capacity SSD are actually struggling with fine-grained page mapping due to the DRAM limitations. State-of-the-art industry solutions adopt 16 KB coarse-grained page mapping to reduce index size. And the latest research work, like the NeFTL, proposed using nano-index. But all these solutions significantly compromise read-write performance. So motivated by this, we leverage LMB through CXL, P2P memory access, or even the PCIe 6 UIO mechanisms. Of course, the PCIe 6 is still not available, but conceptually it can support. So the SSD can keep utilizing the best practice of 4 KB page mapping. So maintaining the best practice and delivering the ideal performance. And the LMB is not simply supplementing the SSD with more DRAM. I believe it provides SSD an opportunity to optimize its index, because the LMB guaranteed that the worst case performance is still good. So in that case, the SSD FTL can use some encoding or new data structures to reduce the L2B table. Because currently the L2B table is simply based on a static array, and for 4 bytes for each page. That's not efficient, because we have observed that the L2B table have shown some segmented continuity features. That means a piece of the logic address corresponds to a continuous piece of the physical address. So with these features, actually, we can do optimizations. So our evaluation with the FAMU SSD emulator demonstrated that the LMB-backed CXL architecture enables ultra-capacity SSD to reduce the onboard DRAM requirement. We did that by reduce the DRAM by 75% compared to the standard drive, but still achieving the optimal performance. This is a significant advantage over existing solutions like the Logic Page or the NAND Index. All these solutions fall short of delivering the ideal performance. And beyond the SSD, LMB can benefit other applications. For the key-value SSD, I believe one very serious issue of the KV SSD is that there's not enough memory inside the SSD for the index. I think with the LMB architecture for the CXL extension, KV SSD can benefit from this architecture. And also the memory semantic SSD, not in concept. But I believe in the future, if we have memory semantic SSD, the memory shortage issue. And the last is the GPU. The LMB adds another memory tier, supplementing GPU memory resource, and may enable the deployment of larger models. These examples highlight the pervasive memory shortages in PCIe devices and demonstrate the versatility of LMB in enhancing PCIe device performance. So in summary, LMB offers a scalable solution to the critical memory challenge faced by ultra-capacity SSDs and GPU systems in data centers. By leveraging the CXL, I believe LMB can significantly enhance the performance of these devices by providing additional memory resource needed to handle today's demanding applications. I believe there are still a lot of work can be done around LMB for more efficient storage and memory solutions. Thank you for attending this session. I'm Tao Lv from DapuStor. I hope you found this presentation helpful and informative, and I'm happy to answer any questions you may have.